Okay, I guess the room got quiet, which means we can start. So, hello. My name is Paul Perkansky. I'm here with my colleagues, Naeem Falandino and Matthew Hollingsworth. We're from DeepField Networks, DeepField Incorporated. And we're here to tell you about building pipelines at scale. So, all right. So DeepField was founded in around 2011 by former Arbor Networks employees. They did some research into the organization of the internet. Who here is familiar with like the topology of the internet or routing protocols or any of that? Anybody? Awesome, cool. So this talk will make a lot of sense to you and will also be interesting to other people as well. So around 2011, around 2010, 2011, we hit sort of an inflection point around the way the internet is organized. So this is the textbook internet, right? This may look familiar to most of you, where it's sort of like a hierarchical model where at the top we have tier 1 networks who serve tier 2 networks, who serve tier 3 networks. And on the periphery is where we have all of our subscribers and all of our websites and things like that, right? And what happened starting around 2005 or 2006 was that the topology of the internet started to change drastically. And our founder, one of our founders, Craig Labovitz, he did some research into how this was being driven by content distribution networks and content providers. So this is how the internet works now, or looks now. So we have actually, content providers such as Facebook, YouTube. We have content distribution networks such as Akamai and Netflix and all these places. They're all right in your network. If you run one of these networks, one of these clouds up here, if you're managing it, you might have Akamai caches, you might have YouTube caches, Facebook peers right directly with you, right? And previous tools for understanding your network, they were really all about, they were developed 10 or 15 years ago, and they're all about networks that look like this, right? So if you're managing one of these clouds here, you're really just concerned with, who am I peering with, traffic going in and out of each of these peering links. Does this all make sense? So when your traffic starts turning into, all these nodes that are within your network, doing all these crazy things, the old tools kind of become obsolete. And to give you an example of that, right around the time of DeepField's founding, what happened was there was a large carrier, one of the largest carriers in the world or in the country, right? And they were in negotiations with one of the largest content providers. I won't name any names, right? But their negotiations started to go sour. And what happened was all this traffic that was going out, reasonably distributed across their peering links and across their interfaces and things, it all started migrating towards these really expensive peering links. It was costing them all sorts of money. And they really had no idea what was going on. They just, their existing tools could really just tell you, there's just traffic going out these peers, and no one knows exactly what it is or why. So DeepField solves this problem of understanding the over-the-top services and everything that's going on in your network from like a service perspective. And the way we do that is that instead of just taking telemetry data from the routers, just collecting sort of where the traffic is going, we do active mining, active scanning. We basically build an index or a model of the entire internet, including all of these caching servers, including all of these peering links, and all of these pieces. And then we merge that, we marry that with all that telemetry data coming back from routers. Like routers will just stream us information about which way traffic's going. And then we can just tell you everything that's going on. And we ingest all sorts of data. So we take like DNS. There's various devices that certain subscriber cable networks have and things like that. And we just put it all together. And the way we do that is with our big data pipeline. And now Matt and Naeem are going to tell you about some of the building blocks of that pipeline.
Hear me? Is it working? No? A little bit higher. All right, there we go. Hi, guys. So I'm Naeem Faladino. I'm the chief data scientist at DeepField. So what that really means is I write software. I deal with UX, visualization, data model, ingest, data warehouse, query, compute, all that kind of stuff. And we have a really cool team of guys like Matt and Paul who help work on various strata of the system. So I am gonna do a high-level overview of some of like the sort of basic tools we use. And so who here knows Python? Good. Who here has used like NumPy? Okay, a couple people. Who's used pandas? A couple other people. Okay, all right, good. This should be mostly useful people then, and then I won't have to belabor Python. Who has used IPython notebooks? A couple people. Okay, good. All right, cool. So, for you and maybe you, some of this might be a little boring at the start. So we're gonna just kind of like start with the basics and move on up, and then we'll do some cooler stuff after that. So everybody can go to that link if you created a Wakari.io account, and there should be a. Do you have the browser up?
Up back there, but
Yeah, there.
the internet is not working great, so
Oh, bummer.
need to
All right.
just try it.
Well, if you go to that link, you should be able to get something like this, and then there's this giant green button here. So once you've created an account, jam on that, log in. It'll copy the notebook I'm using to your account. And let me switch over to my laptop since I've got all that.
What was the link again?
Oh, I took it out pretty quick.
tinyurl.com and then slash MI hackers as one word hyphen workshop. I'll just write it
Yeah,
up.
I gotta do it too. What is it? So,
MI hackers, or yeah,
tiny one word?
url.com slash MI hackers, no hyphen.
Oh, no hyphen?
Yeah.
Okay.
MI hackers hyphen workshop.
Work. Okay.
Okay.
If that doesn't work, let me know.
If that doesn't work, let me know.
All right. Of course, you got to play the fun game where you fiddle with your desktops.
So Wakari is a platform that lets you host an environment that gives you an IPython notebook, which is just a really nice UI for sort of hacking around in Python. It's really good for experiments like this. So for the people who came in now, you'll need to make an account on Wakari.io to follow through with this. If you don't want to, you can always share with somebody in here. It might help. Yeah.
Uh-oh. All right, hold on. Something's not working. Why will that not? All right, hold on. Let me just quit out. Jesus, all right. Great. This is why I authenticated beforehand. I wasn't supposed to have to deal with this. Come on.
I have your notebook up on my laptop if you want to use it.
Do you?
Yeah.
All right, hold on. Wait, I found it. There we go. That's better. Well, actually, you know what? I'll just use yours since I had to kill my server. Nice. Oh, but it's not mirroring. I need to see it. All right, back to the other one.
Yeah.
All right, is it gonna ask me to log in again? No. Okay. Okay. Sweet. All right. That should be the hardest part of this whole thing. Make a little more room too. Okay. So I guess before I turn that off, for most of you, it sounds like haven't used IPython notebooks before. Okay. So Wakari.io is basically like a container platform for running IPython notebooks, which are basically a in-browser way of writing Python and getting like inline output, including like graphs and stuff like that. It's pretty convenient. So you can intersperse it with like Markdown and other kind of like text. So you can basically make these like living code documents, which are nice for this sort of thing. And we use them internally to share analysis and do other stuff like that too. So the quick version of the way these work is you have cells. Cells have a type. The type is here. So this is a Markdown cell with basically an image in it. So if I hit enter, I go into edit mode, which shows that it's got an image. And if I hit control enter, then it executes that cell. And then you got some like Vimy binding. So this is a header cell. This is a Markdown cell. If I go into edit mode here, you can see I got some Markdown text. So, and then if you have code cells, which basically let you write Python code. So I'm going to be focusing on, like I said, NumPy, Pandas, Matplotlib, and then there's a section here, which you guys can look at later on other tools that are sort of like natural extensions. We use, in fact, a lot of the stuff in this second section here at DeepField to basically build, crazy scalable systems. But the underlying components are NumPy and Pandas for a lot of like basically the low-level numerical computing and analysis. So that's why I'm going to focus on that. And then Matt will jump into some of the Hadoop ecosystem stuff. And I think we actually spun up a cluster in our cloud that you guys will be able to connect to and play with in a bit. So, all right. So what is NumPy? NumPy is the genesis of numeric, and then there was another package I can't remember the name of that are basically about. Do you remember what it's called?
Numeric and SciPy, or what?
Not SciPy. There's another one. Doesn't matter. They're basically like array manipulation packages. So dealing with really fast, really big arrays. They compress nicely and have fast vectorized operations on them using like BLAST or some of those other linear algebra toolkits. So all about creating and manipulating arrays. So I'm just gonna go through this without executing it again, since it's all my outputs already created. Then I'll just kind of explain it, and then you guys can run it in your own container. Hopefully that's working for you. If it's not working, then I guess shout. I don't want to derail this too much though, because we have a limited amount of time and a lot of stuff to get through. And then maybe Matt could help too if somebody's having issues. But anyway, basically the way that you do this is you say, I'm importing NumPy as NP. It's just the sort of standard convention. And then I'm going to create an array, pretty basic. And you have to give it a type, right? So a little bit different than normal Python lists, which you don't have to specify the type. It's important to note that basically NumPy arrays are fixed length, just like normal Python lists, and that's one of the reasons that they're so quick. If I say type on it, it's a NumPy array. If I say dtype on it, that'll tell me the actual data type that it's storing, in this case float64. And then you can just output them, and this is basically what it'll look like. So they act like basically well-behaved lists for the most part. You can index into them. You can assign. You can do your normal sort of slice operations. Everybody's familiar with like Python slice operation? Okay. And then you can do your wraparound sort of like indexing too. So if I want to grab the last two elements from the list, I can say -2 : to slice off the end of the list. And then this is where it starts getting a little more interesting. So you can have multi-dimensional NumPy arrays, and it's doing all the hard work for you of basically making this the most efficient thing possible. So here we've got a very small 3x3 matrix, but it's not unheard of to have 50,000 by 50,000 matrices, or you can even go do like million indices, million, with multiple dimensions too, right? So that's 2x2, but that's pretty easy to show here. But you can do very high dimensional arrays or matrices as well, and all of the operations are linearized, so they take nice linear time basically, which is the main reason you want to use this and not normal Python lists. Okay. So if I create that and I say A, it spits it out, looks good. Same sort of deal. You can index into these things, except here you'll use sort of the comma notation for indexing in. So this will grab me the first 0th record or row and first column. And then you can also do slice operations here too. So if I just want to get that first row, I can say 0, nothing, and then slice. And it'll basically leave that dimension unconstrained. So I grab the whole first row. All right. We're going to go a little bit quicker now. Here I'm grabbing a column. So same sort of deal, just the other side. I'm going to grab the middle column basically, and it returns all those values. You can do existence tests. So is 3 an A? Yep. 10 an A? No. And matrices have shapes. So if I say A.shape, it tells me it's a 3x3 matrix. If I say, if I say A range, that basically I can just, it's like calling NumPy array and then saying range 10 in here. So it'll basically make this very simple array. And then if I want to make this maybe like something 2 columns across and 5 rows deep, then I can say A reshape and then give it the tuple of 5, 2, and it will basically take this array here and reshape it into this one. And again, you can do this with high dimensional spaces as well. Easier to reason about it at 2 dimensions though. Filtering. So filtering is pretty sweet. You can do things like really easy to read, like is A greater than 3, right? And it'll basically just return you a mask matrix with all of the false and true values. And then you can use NumPy where clauses. So you could say where A is greater than 3, and it'll basically return you a tuple of arrays that are the indices where the value is greater than 3. So 2, 0 is a value that's greater than 3, 2, 1, 3, 0, et cetera, et cetera. So you can then go and pull those values out. Numerical operations. So I'm going to create another little array here called B, right? So it's got just 2 values in it, -1 and 3. And I can add A and B even though they're not the same size, and you'll get nice output, right? So it'll subtract 1 from every value in this column and add 3 to every value in this column. And I can say multiply, same sort of deal. Won't spend a lot of time on that. Here, if I create a small array called C, which is 1 by 1, and I'm going to interact this 1 by 1 array, or I'm sorry, this just array of 1 or a matrix of 1s with my previous example, then I can say I want to basically add C to B, but I want to control how they're combined, right? Because this has got 2 rows, 2 columns. This has only got 1 row with 2 columns. So you have to specify how you want NumPy to broadcast the additional records into the new set. So really simple, like here, if I say B NumPy new axis, shape. So this is basically saying that I want to shape this array with the columns being the new axis. And then so when I add that, you'll see here we'll get basically subtraction on this side and addition on this side. If I instead reshape it so it's column order, you'll get subtraction across the rows and then addition across rows. All right, pretty basic again. And then NumPy's nice because it allows you to do like math operations across the matrix itself, right? So you can sum across an axis or dimension. So here I'm tallying all of the columns, and here I'm tallying all of the rows. So across, it would take here and add across for the second example and down for the first example. All right. So a few other common things you can do. You can concatenate these things. You can make copies. You can turn them into Python lists, which can be useful for some situations, but you got to be careful because if you've got a 50,000 by 50,000 matrix, then it will eat a lot of memory. Like something that would take 32 meg in a Python list takes about 4 meg in a NumPy array for like float types, I think. So to give you an idea of like how quickly you can blow your memory usage out. And then if you need to write these things out, you can say toString. So lots of nice common operations if you want to get a binary string out and read it back from disk. These are useful for like really quick and dirty serialization. If you're actually working with really big data, you'd want to look at like HDF5, which is a link to it in the additional exploration section. So it's a little complicated for like a really quick if you're not used to dealing with this sort of like data though. So that's why we're focusing on this stuff, which is typically how you process it actually. Like oftentimes you'll take an HDF5 file and then you use PY tables, but many of the operations are very similar. So NumPy provides like a good common denominator for understanding that sort of thing. And so you can read these things back in, right? So same sort of deal, just load this string back in. If you need to deal with special matrices, there's functions for this. You can refer to the docs, but like I can create arrays of just ones, just specifying the shape that I want and the type. Or I can say I want a zeros array like the shape of another array, or multi-dimensional array. And so here it'll just spit out something that's had the same shape as my previous example. If I just need like the identity matrix for some operations or calculations, we can do that. And all right, that's like super boring. It's like arrays, right? So not that fun. But we'll move on to pandas now, which gets a little bit more interesting. So I'm going to load in pandas, same sort of way. I'm just going to tell it that I want to deal with more columns than or a certain number of columns. So here I've just got a normal object that I created, with some cities and a few values, right? Trivial. And then you can create a series out of that. So a series is basically just a way of associating, kind of like tuples, but a little bit more sophisticated. Very similar to NumPy arrays in some ways. But they're nice because you can then do like nice logical operation on them. So if I'm going to say cities, just get me Chicago, Portland, San Francisco, it'll pull those values out. I can say, give me cities where, cities where the the number associated with it is less than 1,000, and it'll just give me that. So then I can save that off to an array, a value, and then I can just index into it using that. So you basically can create these nice masks using logical operations. And it will get me back the mask values. So Austin was true, Boston false, etc. So for, this is assignment, straightforward, same sort of existence stuff. You can check for, null, not a number, that sort of good things. And now we'll shift into data frames. So data frames are collections of series in some ways, basically the right way to put it. And I just got a really straightforward example here with some years, some football teams, number of wins and losses in those years. And I basically tell pandas I want to create a data frame using this object, and then you tell it what columns are, just referring to these indices here. And the cool thing is that IPython notebooks will then spit out like pretty tables for you. So if you're actually working with these things, it gets pretty nice. Couple notes on doing joins. So if I've got two simple frames here with key values of 0 to 5, and this is a key of 2 to 7. This is totally abstract, of course, but and then we have these string values on the left side and the right side. So I get these two data frames that look like this. If I do merge operations, so I can tell it how I want it to actually merge. So merge on my key column, doing an inner join, during a left join, right join, outer. So you basically get some nice looking database type operations, SQL-like operations. And you can see the output here, right? So when I do an inner join, I get something that looks like this, where it basically merged the keys where they matched. If I do left join, it takes the left side, and you'll get nans for where there wasn't a match on the right side. Same for the right, and outer will get both. Okay. If I want to join these together, however, I get something that looks probably not like what I want. So I have to tell concat how I want it to actually organize the data when I concatenate them together. So you can specify the axis to use, and you'll get out something like this, which is probably more like what you want, right? So you basically get the merged data frame of two key columns, left value, right value. Okay, so this is now moving on to a little bit of real data. So this was a file I found. Basically, cities have to publish the public salaries of all the employees that work for the city. So I don't remember what year is this from. It's like within the last couple of years, probably. So in this file, and you'll have it in the bundle package in the Wakari link, there's name, title, department, and salary. So we'll do like a really simple, data mining exercise here to show how you can start using pandas to manipulate some like real data. So most importantly, here's how you get the data in. So I'm going to read the CSV file, pointing to it there. It doesn't have a header. Here's my actual header that I want to use, so I just put the list. And then you can pass in Lambda expressions for converter. So like this salary column, essentially, I want it to go through each value, basically strip the $, and then convert it to a float, so it's an actual number instead of a ugly string. And when I do that, then you can say head, and this is a pretty big file. I don't remember exactly how many it is. It's like tens of thousands of records or something on the order of that. So head will basically get you the first 5 values out of the data frame. So you can see here it's like sorted. It looks by last name. So there's the water rate taker, police officer, chief contract expediter, civil engineer, and there's their salaries. Okay, now this is where it gets, damn, escape key. So in pandas, one of the key features that it has, I think 2 of the most fundamental features in pandas are doing group bys and aggregations. So if you want to sort of combine data in different ways or do filtering on large data sets, this is a nice way to do it. So for example, like if I want to get the counts for each department, right? I can say, okay, so for these values, group everything by department and then save that off. And then from that, give me the size of each record that was returned. So for this department, animal control, there was 68 employees, right? For the board of ethics, there was 9 people. Okay. Data frames are nice. They provide like statistical operations. So I can say, okay, give me the mean for each of those for the head, right? And so it'll go through automatically and calculate the average salary for each department because I've already done the roll-up essentially on the department field. And this is really the fundamental data model we use at DeepField too, right? When we're reasoning about network traffic. If you're trying to provide a sort of ad hoc interface for querying on different sort of data about your network, let's say you want to like constrain yourself to all of your customers in a certain region. And then you want to look at all the different services they're using. So you could say, I want to select out, filter on my Detroit market, and then roll up everything to just the services that they were using. And you'll actually be able to get like, traffic totals out, for each of the different services. If you want to then say, well, okay, that's cool, but I don't want to know the service, and then also what CDN that service was delivered by, because a lot of services maybe are delivered by multiple CDNs. You can then just add a dimension or a column for CDN, and suddenly you'll get the cross product between service and CDN, which will let you say, oh, okay, so this portion of Netflix was delivered by their OpenConnect CDN, and this portion was delivered by Akamai over a peering link or something, right? And you can sort of start to like break down and reason about the traffic in ways that a network engineer or a network security expert would care about. All right, let's keep going. Okay, so other statistical operations. Median, nothing surprising there. So here, if I want to get this is basically the same thing as another example. If I want to order, essentially, the number of unique by the title. So this is for the departments, the number of unique, the number of largest departments sort of descending, right? That's the order ascending false, right? And then I grab the head of that. This now is starting to get into some actual, doing a little bit more analysis, right? So I create a ranker function where what the ranker will do is for the data frame, it'll add a department rank field, which is using this numpy arange function I showed you earlier. And it uses the length of the data frame plus 1 basically to grab the length and basically order all of the employees within the department. So the way that I use that is, so I first sort this data frame by salary and by descending value, and I tell it in place because I want it to do it on that specific data frame rather than returning a new one. Then I can say do a group by department, just like we did before, and I can chain on apply this ranker, right? So apply is basically lets you do an arbitrary function on top of a data set. And in this case, it's basically going to go through and add this department rank value. And since we already sorted it, that's why it can just say what's the length, and then basically blow it out. The cool thing is that here I'm actually doing this whole column at once, right? So I'm creating this numpy array, and then I'm just superimposing the entire array at once rather than iterating over it. So you have to think of these things in terms of full column or join operations. And so then I can do cool things like this. So for Chicago.department rank, where it's 1, get me the first 7 entries. So these are the top 7 highest paid employees in Chicago whenever this data was from, right? And it turns out that, so Rahm Emanuel was the mayor then, or the mayor now, I guess, still. And then, let's see, this Gary McCarthy guy, who was the police superintendent, was actually paid more than him. So you kind of see, and the fall off, right? Mayor, fire commissioner, commissioner of aviation, that's interesting. Corporation counsel, budget director, that's no surprising. That guy's going to be paid a lot. All right. But that's kind of cool. But what if you just want to care about a specific department, right? So this is a data frame. You can actually do database-like operations on top of it. So I can say Chicago.department where it's law, and then give me the last 5, right? So I can find who are the least paid employees in the law department, right? And it turns out they're all still doing pretty well. But it's kind of cool though. Corporation counsel, city prosecutor. There's probably not a ton of people in the department, though. You'd think a city like Chicago would have a lot of employees, though. This might have just been people who work at City Hall and not the whole city. Otherwise, it'd be grounds department would be number 1 or something, probably. Okay, so actually, I think that is what it was. Okay, so we'll shift gears now, and we'll do a little bit more involved example now that we can have some basis on how to do group bys and aggregations and apply functions and things like that. So this is a data set called Movie Lens, which has a bunch of movies, a bunch of ratings, and a bunch of users who gave ratings, essentially, for, I don't know, a large slew of movies. I guess I could figure it out. Let's see. Come on. Typesetting math, my ass. Just look at the whole thing. Oh, I didn't execute the whole thing. All right, 1 second. Turns out you have to run your code to make it. Man, the PD's not defined. Come on. Oh, Yeah, just run all. Just run all my data. So IPython notebooks will save the output from the previous run, but it hasn't actually executed all those values into its internal state. So now I've just said go ahead and rerun everything, so I should actually have all those variables defined. Okay, so yeah, here's movies now, okay? And you can see like IPython notebook did a nice job of like scrolling this whole thing for me. It's gonna be big, so let's see, oops. Yeah, there's like, okay, like 1,600 movies. That's cool. Okay, so here's like basically what it looks like, right? We've got a movie ID, the title, the release date. This is apparently null, and the IMDb URL, which is basically fine. A word about index resetting. So when you're doing lots of operations like this, oftentimes, like a database, you want to set what your indexed value is so that you can do operations on it. And because I care about speed and I just want to do this stuff all in place rather than making lots of copies, you'll see this in place true flag sprinkled around. And oftentimes I'll need to say reset the index on this data frame so that I can then do another set index operation, basically change how my data is indexed. Internally what that's doing is it's building trees to organize everything in the most efficient way for the way that you want to reason on it. So it's actually repartitioning your data frame under the hood. And that's just one of the really nice things about the way Pandas works. So this is what my users looks like, right? Same sort of thing. I've got index, age, sex, occupation, zip code, and I can say describe. Now this is super useful. So it'll go through automatically. And now index is not very useful because who cares about the mean of your array indices? But for the age, it'll actually go through and say, okay, well there was 900. Some is actually not useful in that situation either. I guess if you cared about like the combined living years of all the people who were in your system. But the average user age is like 34. The standard deviation is 12. The youngest person was 7. 75th percentile was 43. The oldest person was 73. So it's like a quick way to get like stats out, from a data frame. And then you can do nice combined operations, right? So I can say users where the age is 40 and it was male, then that's your list, right? So boom, got the numbers. What about like women or where they're under the age of 30, right? So that's a much larger list, right? In fact, it went ahead and truncated some of the values for me. There was, turns out, 565 results. Okay, that's good. That'll come in helpful in a little bit. So next, we'll go into this lens value. And I went by kind of quick because I was trying to show this thing off. So I basically went through all these things were in separate segments of these different files that were like pipe separated. So I read them all in, and then I merged. I used my Pandas merge operation to basically merge the movies with the ratings. And then I did a final merge between the movies ratings and the users to get the complete table. So that's lens, which stands for movie lens. So then when I go down here to lens, I can say, okay, for lens, group by, and then tally, sort descending, give me the top 25. These are the top 25 most rated movies in the data set. So Star Wars had 583 ratings, Contact had a 509, Fargo, etc. So that's cool. Now what if I want to do it a little bit cleaner, right? Because this is a little bit verbose, right? I do group by and size, and then say sort, and then do the slice operation. I could just say lens title, because you can index into dimensions in a data frame, and just using dot notation, and then give me the value counts, and then slice on the top 25 again. So same sort of thing, just a little bit more concise way of saying it. All right. Now, I think I've maybe got like another minute or two, so let's blitz through this. So lens, I'm going to group by the titles now, and this is the next big thing that Pandas is really good at, is running aggregations. So here, I'm saying I want to create an aggregation on this grouped data set, and I'm basically generating a new column, or a new aggregation called rating, which runs these two functions on top of it, right? So I'm going to say numpy calculate the size and numpy calculate the mean of those arrays that we're grouping by. And basically that spits out this. So till there was you had 9 ratings with a mean vote of 233. So now I'm actually starting to aggregate the ratings and calculate some stats on them. Okay, so what if I want to sort them now? So I can say sort by the tuple of rating and mean. So I'm sorting on multiple columns now at the same time, like doing a multi-level sort, ascending false. And that's kind of useful. Now I'm like getting all of the straight 5s at the top, but this is like a rating of 5 with one person loved this movie. So that's kind of not the most useful thing in the world, right? Star Kid down here had 3 votes. I mean, I think I remember that movie. It was definitely not a 5. It came out when I was in high school. So, all right. Now, what if I want to say, all right, well, doing just a pure sort on this doesn't work, right? So now I want at least there was 100 votes, right? At least 100 ratings. So movie stats, ratings, size. Quick word about the size variable. I have to use this sort of notation because size is sort of a keyword in pandas. So in this case, I actually want my column size, not the array size. So here, by doing this and saying where greater than or equal to 100, this creates one of those mask arrays that I showed like right at the very beginning. So this is now the mask of at least 100. And then I can just say, so movie stats, index in to at least 100, and now sort it by rating and mean ascending false, and give me the first 15. Okay, now I've got the highest rated movies that had at least 100 votes. So A Close Shave, which came out in 1995, apparently. Well loved amongst the people that saw it. I was not one of them. Schindler's List then was pretty high, good number of votes. The Wrong Trousers, man, there's some terrible movies in here. Casablanca, Shawshank Redemption. Really? I haven't seen it. Oh, okay. All right, you're right. I was thinking something else. Yeah, that is pretty good. Yeah, and then there's some other stuff in here that's pretty, you expect, right? Usual Suspects, Shawshank Redemption. So, okay, now we're actually getting to something useful, right? And this is typically how this stuff will work, right? You'll just okay, give me a bunch of data, clean the data, merge the data, start massaging and playing with the data, find useful stuff, extrapolate, do more. Okay, so now let's keep going. Let's get the most 50 rated. So we'll just grab those real quick. This is just exactly like we did before. And now we'll do a few plots. And Pandas has a cool plotting library. I only have a couple plots in here just because, I don't know, I just only have a couple, but it'll be giving you enough to get you started. This is important though, right? So when I import matplotlib, you want to use this percent thing here. So this is what's called a magic function to IPython notebooks. And you're basically saying hey, IPython notebook, I want you to inline my matplotlib graphs, right? And so that's really helpful. And then I'm just setting an option, I want to use a better styling function. So here, if I go onto my users object, this is just the plain Jane users file I loaded earlier into a data frame. And I say, okay, for the age, give me a histogram with 30 bins. And then I can add a few labels to my plot. PLT is a special variable that Pandas will assign to when you're doing interactive, like in an interactive shell, building graphs. And IPython Notebook is really cool and smart, and it just says, okay, cool, here you go. Here's your histogram of all of your binned user ages. Okay, then what if I want to construct my age groups myself? So now I can say, okay, well, here's my labels, right? So these are going to be my groups. And then the way that I do this, these are grouped by 10, right? So 0 to 9, 10 to 19. So now I just say, all right, give me here, we'll talk about this part first, right? So I'm going to generate an array from 0 to 81 with a stride of 10. So it'll sort of skip, And then I'm telling Pandas that I want to cut this data frame by the age property using these labels, and then select out age and age group, which is my new column that I added here from the cut, and then drop duplicates. So basically I'm filling in the age group from these values based on age column. All right. Drop the duplicates, give me the first 10. All right, so now you can see the age, and then it matches up with the age group. That's nice. Now I want to run an aggregation function on this. So group by age group, right? So do my group by, my normal group by, then do my my rating aggregation for the count and the mean. And you can start to see, okay, cool, well, this is how the different age groups vote, right? So there was 43 votes from people who were under 10 years of age, and they tended to vote from about this, right? And they have like a higher number. They really like the stuff they see. They're like, oh man, probably because I've only seen like 5 movies, so they're all awesome. And then people get a little more cantankerous and picky. And then, 30s, people start getting a little more happy about the stuff they see. And then people get kind of bitchy again when they get old. So that's kind of interesting. Now I'm going to do like my index reset and then reset my index on the movie ID. So now I'm repivoting or reselecting the index. And now I'm going to grab out this. Remember I had this most 50 before? So index is like the value that like maps into each record, right? So I can say, all right, within the full lens, grab me these index values, then group it by the title and the age group, then calculate the mean on the rating field and grab me the first. All right, this is now like legitimately pretty cool. Like we've synthesized all these different parts, and you can start to see, oh, okay, so for Air Force One, this is like alphabetized, right? These were the different age groups, and this is how people rated, right? So everybody felt basically about the same about Air Force One, except people in 50-59 bracket, probably because they love Harrison Ford, or the president, or America, or something. And then like Alien, right? Like younger people were like, oh, hell yeah, this is great. And then like kind of moderates in this group. And then there's this spike, and that's kind of interesting, right? Like actually the highest population was like people who were 50-59. So maybe we would need to like, this would be a thing I'd be like, well, that doesn't fit the trend. So, if I was actually looking at this, I would probably go get the counts to see if there was like a low number in that bracket. Like it could just be that, there was like, there's 2 people like, and they just happen to be sci-fi buffs who were like, oh man, this Alien movie is gonna be amazing, and they go check it out, right? And
it came out when they were younger. They remember it.
It could be. It could be. Yeah. So so now like same sort of deal, right? By age, I'm going to take that same sort of by age like view of the data, and I'm going to say, all right, for the rating, give me the mean, and then unstack them essentially so that I create like a new data frame based on this index, and then fill where there's not a value with 0, and then just for kicks, I grabbed like the 10 through 20th, so we don't always see the same movies again. So here now you can see for ET, this is just like a nicer way of presenting it, right? So rather than having to read it down, you can kind of read across the row, right? So unstack basically like shifts it. All right, and then for like our final sort of the piece de la resistance, we're going to reset our index again. Now we're going to actually create a pivot table. So who's used pivot tables like in Excel or? Okay, they're actually super useful to do all kinds of cool like roll-ups on different data. So we say, all right, pivot by these indexes. So basically we're grouping by those 2 things. And then this is the column I want out. And then I want my rating to be based on, the value to be based on the rating. And then this is just to fill when there's not a value. And suddenly now I can get breakdowns by like, movie and then see the gender bias, right? So, males tended to like Toy Story a little bit more. Females tended to like Goldeneye a little more, which is interesting, but true, apparently. 4 Rooms, men definitely liked it more. It's like, who's seen 4 Rooms? It's awesome. This is a good movie. Quentin Tarantino did like one of the segments in it. It's pretty fun. I think like, I don't know. Anyway, we'll move on. So, and then you can do like cool matrix operations on these things too, right? So if I can take my pivoted data table and I want to say, okay, for the male minus the female, give me the difference, right? So calculate the difference between the gender bias. And now I can start to see, okay, this is where people were off in terms of like, there was like, in this case, right, like so men like this one more, so it's positive. In this case, women liked it more, so it's negative. It's just the way the ordering was. And then finally, I can do, this is the last one, it's so good. So good. So pivoted, get me the movie ID, then select is in. So I'm going to grab my 50 most viewed movies or most rated movies, pull those out of my pivot table, select the diff column, and that's now my disagreement. So that's where people were like, didn't have an agreement on the, what the video, the movie, how good it was. Now I want to order those and then do a plot, a horizontal bar plot. So that's bar H, and this is my figure size, and then add some titles and labels to it, and then boom, right? So here you can see the male versus female average rating, where the difference is greater than 0 is favored by men. So The Terminator, 1984. One of the best movies of all time, in my opinion, because I'm a man, maybe, had the biggest discrepancies. So women really did not like this movie. And my axis down here is like, yeah, it like differed by like more than half a point, which is, for this case, for this data set, pretty significant, right? As you can see up here, there's a lot that were like, off by a very small amount. Let's jump down a little bit, right? Let's just go to the top. So Terminator, Aliens, Aliens, then The Empire Strikes Back. All good, all good. All right, now we'll go to the middle. So what did people most agree on? So this is interesting to me, right? Return of the Jedi, everybody kind of liked it the same amount, but Empire Strikes Back was like, men liked it a lot more. It's weird, I don't know. Does that mean women have bad taste in movies? Like Empire Strikes Back was so much better. That can't be the case, that can't be the case. So there must be something else going on. Everybody else also basically liked E.T., Indiana Jones and Last Crusade. LucasArts really hit it out of the park. Lucasfilm, I guess. And then down here, see, this is, I don't know, like, okay, Titanic, yeah. Apollo 13, Twister, wow. That movie was something. Mission Impossible, Schindler's List, Mr. Holland's Opus, that was a legitimately really good movie. The Rock, The Birdcage, that was also a really good movie. And then this one made no sense to me, right? Independence Day, right? I don't know, maybe this is like belies some sort of underlying, women love national security and like, we're gonna go out, we're gonna like punch the aliens in the face with our president in his fighter jet, If nobody's seen that movie, it's ridiculous and fun. Okay. All right, so that's it. That was a lot. I know it was a slog at the beginning because I had to teach you about how to deal with arrays and the stupid thing, but this is all like the same sort of principle, right? We do this the same way, basically substitute 3 by 3 or 10 by whatever, 10 by 1500 for 100 by 10 trillion. That's essentially what we do. Trillions maybe a little bit overstepping it, but we do deal with. I don't know. I don't know. Yeah, billions of records a day. Yeah. For what? For the whole 24 period?
For yeah, right.
Yeah. Okay. Yeah. So one of our big customers does about 24 billion records a day. So it's pretty good. We deal with some scale.
When we're at this stage, it's a lot more than that when it's at the raw stage.
Yeah. Oh, that's after we've like culled a lot of the low-level data. All right. Anyway, cool. Well, you guys all have that in your Wakari thing, so you can go like fiddle with it later and like just hack around with it and see how it works. So hopefully that was useful. I appreciate you guys hanging with me there for a bit. And now we'll do something hopefully even more interesting with some cluster stuff. What did you spin up, by the way? For I have to give you that mic.
It's a 6-node thing in EC2.
Like
it's
8X's or?
They're M1 larges.
Oh, okay. All right.
Smallest I could get by with. Okay. But I just went for quantity instead of quality. Huh. All right. Everybody hear me? Okay. Cool. All right. So back to the slides here. All right. So what Naeem just told you about is how we actually do the low-level numerical analysis when we're crunching numbers and all that sort of stuff. But the thing that we do at a higher level to manage all of this sort of stuff across many nodes and whatever is Hadoop. So Hadoop, the fact is that distributed computing is hard. I don't know what courses you guys take on this, if any. I didn't go to school here, but it's a very challenging problem because you have to deal with like getting data across different nodes. You have to actually coordinate all the nodes working. Computers crash when you have clusters with like 500 computers or whatever. It's basically every day one of them is going to die. Likely it's going to die in the middle of your job, therefore you have to be able to deal with failures and that sort of thing. So distributed computing is hard, and Hadoop doesn't really change that, but what it does is it does a very clever thing, which is it makes the difficult part offloaded onto the ops people. So you don't have to develop software. So we all like that because it makes our lives easier and all that sort of stuff, but it's unless you're going into ops. So if you're going into ops, don't do Hadoop. It's a pain in the butt. So anyway, they do a very smart thing by offloading onto the ops people. Basically, they give you this interface that you can sit there and watch and say whether it's running or not. And it solves a lot of the really hard problems, so you don't have to solve it in your own software, and so you don't have to reinvent the wheel every time you move to a new project. So
Reinvent the wheel. Terrible idea.
it's a terrible idea. So the question is, how does it help? The first problem it solves, and this I will say, this comes from I took selections out of a much larger talk. I'm going to be giving you two problems, basically. This is the first. We'll get to the second in a second. The first problem it solves is distributed data access. So as I was mentioning, ideally, when you're doing computation, you want to try to minimize the amount of network traffic that you have, because that's oftentimes the bottleneck when you're doing distributed computing. You have to get, if you have 200 nodes and all 200 nodes need data on all the other 200 nodes, then it overwhelms the network, and that becomes your bottleneck very quickly. So you want something that can manage the distribution of files and data to different machines. And in particular, what you want is you want that system, you want to try to bring the computation to the data rather than the other way around, so that it's cheap to move code around because it's going to be on the order of megabytes, whereas the data you're analyzing can be on the order of terabytes. So if you ship code around to where the data is, you're better off. So Hadoop's solution is something called a HDFS, Hadoop File System, Hadoop Distributed File System. Basically, it acts exactly like a command line utility does for on the command line. There's ls, make dir, put and get are different because you have to actually upload it to the distributed file system. But cat, rm, all those sort of stuff are the same. So what this is doing here, instead of doing ls and make dir and all that on your local file system, you're doing it on the Hadoop file system, which is available on all nodes on the cluster. So you can run ls on node A, and on node B it'll give you the same result because it's running against the same file system. But because it's not the local file system, you have to upload your data, and that's what the put and get are doing. Like, they go from your local file system up into HDFS. So there's a CLI for it. There's also different APIs, including Python APIs. So the Python API to use is Snakebite. This is weird. Yeah, feedback's probably my phone. Let's take that out. Yeah, so there are APIs for it to make it so that you can do it from different programming languages. In Python, it's Snakebite. They have a really nice API for that. Also, Snakebite has a nice command line utility. There's a good reason to use that. HDFS, the HDFS command is actually spinning up a Java JVM every time you run it, and so it's going to take at least 3 seconds typically. So just to show a comparison here, it took about 3 seconds to do HDFS DFS list, and whereas Snakebite took much less than a second. So it's advantageous to use Snakebite in this case. It's a lot faster and does the same thing that the HDFS stuff does, just takes less time. So there's a Python API, there's a Python CLI, there's also Java API, but if any of you guys use Java, that's about what it looks like, so we'll just forget that. I'll give you a 30-second overview about what's going on behind the scenes so you can know what breaks when you use it, and then we're going to move on to the next one and you can play with it. So HDFS has name nodes, which is basically the thing that keeps up with the metadata for all the files. So if you create a file named foo, you tell the name node you created the file, but it doesn't actually store it there. It stores it on the data nodes. And so it says there's a file named foo. I'm going to put 10% of it on node A, 10% of it on node B, et cetera, and it distributes it, replicates it, all that sort of stuff. So Hadoop has failover built in. If you lose one of the nodes, according to your replication factor, you either don't lose data or you do if you have a replication factor of 1, but it's just a configuration variable inside of HDFS. So if you say replication factor 4, it will actually take that 10% block that it generated and put it on 4 different nodes. So if you lose any one of them, it doesn't really matter. So HDFS, you talk to the name node, you tell it, I want to put a file in. The name node then distributes all of the blocks that it creates blocks out of the file that you send and then distributes them to all the data nodes. And in replicas according to how you've configured it. So the client talks to the name node tells you where to find the data, and then you download the data from the data nodes. So the second problem Hadoop addresses is distributed computation. The one you might most likely have heard of is MapReduce. So, but Hadoop actually has 2 solutions for it right now, MapReduce and Spark. I will give you a quick overview about what MapReduce is, just in case you haven't heard of it. So MapReduce is inspired by map and reduce functions present in many languages. This is what those functions look like in Python. So you give it an iterable as the second argument, and the first argument is a function to run over that iterable. So the return value of map in that case is 149. It mapped over, it basically squared 1, 2, and 3, and so you get 149. And then the reduce function basically aggregates all of those together. So in this case, I said add them, and you get the sum of all of them. So this is very nice because map, as you may notice, that you don't care about there's no coupling between the different elements. You could imagine that you could run 1 squared on one node, 2 squared on another node, and 3 squared on another node. It's all separate, and they can all be returned independently that way, so therefore it lends itself well to a distributed computation model. So basically, map is easily sharded out to different nodes, and then reduce, you can reduce whatever that node mapped into one piece, then the other nodes into one piece, and then do one final combine that will only have to have as many operations as there are nodes. So that's something that Hadoop lets you do. But I actually won't talk much more about that because MapReduce in Hadoop is sort of the old style way of doing it. The thing that's actually called MapReduce is an old way of doing it. It has a lot of disadvantages, namely, like each mapper and each reducer has its own JVM, so it takes a really long time to spin up. Also, if you want to run a whole bunch of map and reduces in sequence, there's no way to not write out the intermediary results to HDFS, so it takes a really long time. Like just in general, MapReduce takes a long time because of that intermediate computation like storage to HDFS. So Spark is the new way of doing things. Basically, you can build up a DAG of different maps or reduces or operations or whatever. DAG standing for directed acyclic graph. So you can make a plan of work, and it does all of it in memory and then just spits out the result at the end. And also the model that it uses, it doesn't spin up a JVM for every single operation it's doing. It's all inside of a permanent daemon that's sitting there and running, and so it spins up immediately and you don't have to worry about JVMs. So what Spark looks like, I'll just give you a quick example of it. So the API is such, you basically define the input, where in this case file would mean in Spark parlance, it's a resilient distributed data set, which basically just means it's something that has been split out amongst a whole bunch of different nodes and is immutable, so you can't change it after it's been defined. But that doesn't mean you can't transform it, so that's what the next stuff does. Flat map here, you give it a function that says for each element inside of that text file, which the way the API works, each line is an element. So for each line, I want you to split it, which in Python does it based on white space by default, and then map over that. So turn each of those words that it split out in the first step into the word and 1 as a tuple. And then you reduce that by key, which in this case, the key is the left-hand side of the tuple, so the word. So it calls reduce, and then it basically adds all of those up. So the result would be the number of occurrences of a particular word. The cool thing that you can do with Spark that you can't do with MapReduce is that you can actually, at each of these steps, you can split off in multiple directions, do one map. So like in this case, there's an intermediate result where the intermediate result is a list of all the words, and then I can do two separate things. In one path, I can just do the same reduction that I did before, and in the other path, I can filter it first, looking for only capital Buffalo versus not capital Buffalo. If you aren't familiar with Buffalo, 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 you should look that up. It's kind of funny. It's an actual sentence. So anyway, so Spark is more flexible. If you end up running into Hadoop, I would suggest using that instead of MapReduce.
This looks better on a resume these days.
Yes, it looks better. It's definitely more flexible and more interesting to work with. As I mentioned, this was part of a much bigger talk. The Hadoop ecosystem is humongous. There are a lot of really cool pieces to it, all worth looking at. The only things that we talked about very briefly here are HDFS and Spark, which is there in the middle. But all of these other things are definitely worth looking into. About half of them are alternatives for basically for Spark, computational models, things to help or plan or whatever. And the other half are persistence, like HBase and Avro and all those. So there's lots of cool things. And there are also lots of cool Hadoop distributions. Each of these have their advantages. I would say that Hortonworks and Cloudera are the main ones you'd want to look at. As I said, it's basically the whole idea behind Hadoop is to shove off the difficult things onto the ops people. So it's very difficult to get your own cluster up and running. It can take a long time, and that's why these distributions are there. But even then, it takes several hours, or you have ops people that have scripts to do it for you. But like, if you go and follow their instructions, it will take you at least several hours to get a cluster up and running. And even then, like, if you don't know what you're doing, it's probably not actually running. You just think it's running. So, but anyway, these guys help with that, but they don't take the problem away. If you don't use one of the distributions and you try to roll your own, you will be there for weeks. So like, if you ever do this, don't just go to Hadoop's site and download it. Go to one of these guys' sites and download their stuff, because it will save you many hours. It'll still take many hours, but it'll save you a long time. All right, so the rest of this is going to be a free-form, like, whatever you're interested in about Hadoop, ask me. I have spun up a cluster for you guys so you can log in. There's, at the top there, shows you how you can SSH. The 1 to 6 means that you can pick 1, 2, 3, 4, 5, or 6 there. The password is DeepField with an exclamation point. And the -L there is tunneling a Hue server, which is basically like IPython notebook, but for Hadoop. So you can try that out too. I made a couple of examples. Those examples are only available on the first node, but if all of you log into the first node, it'll probably die. So like maybe copy them off or something if you want to do that. But I have a couple of examples there. And you run the examples that I have there using a command that looks like that. All right, and so that's that. I'll just be like walking around. If any of you guys are interested in learning more about Hadoop or anything like that, then I'm more than happy to show you how to use it. And we're hiring, so if you're interested in working on this stuff as an internship or whatever, just let us know.
There's lots of